Hello, this is Sheikh Hannu. I am pursuing BTech second year in VVITU. I am from ECE department. My roll number is 24PQ1804E9. I am from C section. Mm, Today we are going to discuss in the switching theory and logic design. Subject is also known as STLD. The fourth unit is a sequential circuit. The one of the main topic is the counters. Mm, Okay, see the mm, Okay, first of all, see the what is a counter in a digital electronics. How the counters are how the counters are act in digital electronics and what are the aspects and what are the advantages and the disadvantages are also we are discussed. Okay, in digital electronic, at its core, a counter is a sequential logic circuit designed to track and display the number of clock pulses or events it receives. This fundamental component forms the backbone of various digital systems. Mm, Counters are essentially sequential logic circuits that incrementally count Input clock pulses, often operating asynchronously. Their functionality is crucial for a wide array of applications, from a basic timing mechanisms to complex data processing. Okay, see the one of the imaginary diagram of digital electronics encounters. There are indiscernible unit devices such as the digital timers, precision clocks, frequency dividers for signal processing, and a robust event counters in the industrial and the scientific equipment. Okay. Mm. See we know that there are two types of counters. The counters are divided into two types. The first one is asynchronous counters, and the second one is synchronous counters. We know that the synchronous counters are also known as a ripple counters. Mm, See these counters are characterized by a cascade arrangement. The synchronous counters are arranged by a cascade where flip-flops are triggered sequentially. In this, the flip-flops are triggered sequentially. Okay, sequentially means one after another, another after another. Okay, one after another, creating a ripple effect as the count propagates. See the next one is a synchronous counter. In in contrast, synchronous counters ensures that all flip-flops within the circuit are triggered simultaneously by a common clock signal, leading to faster and more predictable operation. Okay. See the diagrams of asynchronous counters and asynchronous counters. Mm, and the next one is synchronous counters. See the clear cut explanation about the synchronous and the asynchronous counter. First of all, see the synchronous counter. Unlike their asynchronous counterparts, synchronous counters are designed for precision and speed. All flip-flops receive the clock pulse simultaneously from a common clock source. This parallel triggering eliminates the cumulative propagation delay, ripple factor inherent in asynchronous designs, and resulting in a minimal propagation delay and a significantly faster operation. While synchronous counter offer superior performance, they typically require more complex design due to the additional logic gates need to ensure proper state transition, prevent race and conditions. Okay. Mm. The next one is the asynchronous counter, also known as a ripple factor. In a synchronous counter, the clock pulse is directly applied only to the first flip-flop. The output of the flip-flop this serves as a clock input for the next and so on, creating a ripple of a toggling state across the chain. Okay, this sequential triggering means that each flip-flop toggles in response to the preceding one. When this design is simple at a lower power, the inherent propagation delay accumulates with each other, leading to slower operation, especially in larger counters. Okay, see we know that the counters are classified into two types based on the modulus. condition, modules, and counting style. Counters are further classified based on their modules, value, and counting direction, other flexibility for various design requirements. Non-truncated counters and the truncated counters. The synchronous and asynchronous are again divided or again subdivided into non-truncated counters, and the second one is the truncated counters. First of all, see the non-truncated counters. Count through all possible states up to 2 power n for n flip-flops. Truncated. Instead of truncated, designed to count to a specific value less than or equal to 2 power n. Okay. Mm, the mod value of a counter defines the total number of unique. It can be unique means it cannot be matched with any other. Okay, state that it can be cycled through before repeating. This value is always, let's say, less than or equal to 2 power n, where n is the number of flip-flops, small n. Okay, the we we see that truncated and the non-truncated counters are also again subdivided into three types. There are up counters, down counters, up down counters. See the directions of up counter. It is a up direction. See the down counters. It is going to down. See the up down. It is also up counter and as well have the down counter. See the arrow marker. You see. Up counters increment their count with each clock pulse. Down counters decrement their count with each other clock pulse. Up down, a count clock both and a down controlled by an input signal. Hmm? Okay. See the key differences of a counters. Hmm. There are five aspects, key differences like power, accuracy, complexity, speed, clocking. See the clocking. Asynchronous counters utilize cascade clocks where each flip-flop's output triggers the next synchronous counters. However, employ a common clock that triggers all flip-flops simultaneously. Okay. See the speed. Synchronous counters operate significantly faster due to their simultaneous triggering mechanism, which eliminates propagation delays. Asynchronous counters are slower due to the ripple effect. The third aspect is the third difference is the complexity. Asynchronous counters are simpler in design and require fewer components. Synchronous counters are more complex, necessitating additional logic gates for synchronized operation. And the third one is accuracy. Accuracy. Mm, Asynchronous counters produce fewer timing errors and are more reliable for precision counting tasks. Asynchronous counters can exhibit timing inaccuracies at higher frequencies. The fifth key difference is power. Asynchronous counters generally consume less power, making suitable for battery operated device or low power applications. Okay, we have see the key differences between the counters in five aspects like clocking, speed, complexity, accuracy, and power. Okay, let's see some real world applications of counters. In real world applications of asynchronous counters, basic digital clocks. The second one is a simple event counters in less critical system. Third one is a time delay circuits. Fourth one is a low frequency divisions. See the synchronous counter applications, high speed timer in a microcontrollers, a computer memory addresses counters, precise frequency divider in a processors, digital signal processing DSP. These all applications are based on the balancing factors like speed, complexity, and power efficiency. These are all these three factors like speed, complexity, and power efficiency. These three main these three main factors are also based on the real world applications of counters. They are also play the key role. Okay, see the see the applications diagrams of asynchronous and synchronous counters. This one is asynchronous, this one is asynchronous. Okay. Okay, let's see the why we choose over the other. We have the various options like another counters, but why we choose this only? See, the decision to implement either an asynchronous or synchronous counter is a strategic one, driven by the core requirements of the digital system being designed. Okay, see the if you see the asynchronous counter, simplicity and efficiency. Optimizing for asynchronous counters where the primary concerns are design simplicity, low power consumption, and cost effectiveness. Partially for applications that do not demand high speed operation for extreme timing precision. Okay. See the another one, asynchronous counters, speed and precision. Choose synchronous counters when speed, precision, and reliability are paramount. Their synchronized operation makes them indisciplinable for complex, high-performance digital systems where timing accuracy is non-negotiable. Okay. Mm. See the counters, counter powers in digital systems. See, let's see the counters in the case of digital systems. Okay, there are the two: a fundamental rule, strategic rule, a performance impact. Performance impact. Okay. Mm. Let's see the counters are foundational elements in digital electronics, playing a vital role in transforming raw clock pulses into structured meaningful counts. Okay, if we see the three counter power digital system, first one is a fundamental rule. Counters are essential sequential circuit that converts discrete pulses to countable events, enabling timing, sequencing, and control in a digital systems. Okay, and another one aspect is a strategic choice. A clear understanding of synchronous versus asynchronous counter types is crucial for optimizing digital circuit designs, ensuring efficiency and functionality. And the third aspect is a performance impact. Performance impact. The correct counter selection is directly enhances the performance, efficiency, and accuracy of electronic systems, making it to a key decision understanding. Hmm? Ultimately, the judicious choice and implementation, the right counter type can significantly boost the overall performance, efficiency, and accuracy of an electronic device or system. Okay, see the see the diagram. Mm, we are also seeing the why choose one over the other. And the second aspect is the real world applications, some real world applications about the counters. We are also seeing the what is a counter and how many types are there counters like synchronous, asynchronous, and what and a clear cut explanation about the synchronous counter and as well as the asynchronous counter and their diagrams and how they operate and what are the conditions that we have to implement while doing the operation of counters. Okay, the synchronous and asynchronous counters are also again subdivided into two types. We know that they are truncated as well as the non-truncated. These are also the two aspects. We know that the mod value is should be less than or equal to 2 power n. 2 power n. We know that the 2 is a constant value and the n is a number of flip-flops. Okay, number of flip-flops. If we see again the truncated and the non-truncated counters are also again divided into three subdivisions like up counters, second one is down counters, and the third one is up down counters. If we see the arrow mark direction of the up counters and it is up, and the down counters arrow mark direction is down, it is down, and the up down arrow mark is 1 per, and it is a up down and as well as the down counter. Okay, it has arrow mark like up and down. Okay, next we see the some key aspects of key difference. of about the counters in in the case of a clocking, precision, complexity, speed, accuracy, power. Okay, power. If we also see the okay, we discussed about the 2 power n mod value. Mm, Mod value 2 power n. Mm, wait. Mm, if we see that the ripple factor, the asynchronous counters are also known as a ripple factor. Okay, see the diagram of see the okay, see the diagram of this logical diagram. There are some inputs and as well as the output of the asynchronous counter ripple factor. Okay, mm, this is also one of the diagram of the synchronous counter. Asynchronous counter. Okay, see these are the some simpler simplest diagrams of asynchronous counters and as well as the synchronous counter. See that. See the diagram of the asynchronous counter. It is like a rectangle shape and the square shape, and we have the clock pulse also. And the see the synchronous counter. It is like a clock shape with the synchronous behavior with the synchronous behavior. Okay, okay, okay. These all are about the counters in sequential circuit. In sequential circuit in switching theory and logic design. Okay, in switching theory and logic design. Attending.